Welcome to the optical communication course. Today we will learn that a polarization mode dispersion. So we have seen that intermodal dispersion and intramodal dispersion earlier. So that is about a intramodal dispersion. It will be most affect to the single mode fiber if we have a intramodal dispersion, and intermodal dispersion, that will be zero for the single mode dispersion, single mode fiber, but for the multimode fiber it will be effective here. So to reduce the intermodal dispersion, we need to use a refractive index profile. Okay, that refractive index profile, that will be a parabolic one. So in a multimode fiber, there are the two types of fiber: a step index fiber and a graded index fiber. So now if we use a graded index fiber, so we can minimize the intermodal dispersion. Now waveguide dispersion is again a one more factor here. So in which why this dispersion occur? Because of that you a source we have, and that source has a spectral width. A source has a spectral width, and that spectral width will be large. Because we are using a multimode fiber, so then they have the largest spectral width. And that spectral width means what? That each and every component belongs to a different frequency number or a different wavelength. Because of there is a phase difference, or because of there is a phase delay, we'll talk phase difference later. Because of that phase delay, so then that velocity of each and every component will be changes. Some of the frequency component we say that f1 to fn, so that last frequency component will reach first and first component will reach last. Means you can say that the slowest frequency, slowest mode, or a you can say that is fastest mode. When there is a difference in the frequency component, they will reach with a different particular period. So that's why because of that a pulse broadening takes place. Now that pulse broadening means what? For a given input pulse we have, so it will reduces the output amplitude as well as it will broaden the pulse. So that is about a pulse broadening, and that pulse broadening because of a that group delay. Okay, because of the group difference in a group delay for the different modes. So due to that, there will be a difference in a velocity. So as we have seen earlier, why this dispersion occur? Because we say that a dispersion in a particular fiber, and that will be depending upon that a refractive index component. So refractive index component means what? We can say that that ratio, we can say that refractive index with respect to the wavelength is not equal to 0. So that's why that dispersion occurs. So now that dispersion because of that phase velocity for the given particular mode. If it is a intramodal dispersion, phase velocity will be changes, or you can say that whenever we can say that a mode is propagating through the fiber, in that case, for a source, they have the various spectral components. Because of that various spectral components, that when we say that for a given particular fiber, we say when a power launch inside the fiber, for a given particular source, that they have the various spectral component. So for a spectral component, difference in a spectral component we have, for a given particular source, and different various spectral components will be launched inside the particular fiber. So that's why there will be a pulse spread occur because of that group delay in the optical fiber. And that particular group delay, we can say that that will be depending upon the velocity of the your rays propagating through the fiber. And that velocity is reciprocal of that group delay is reciprocal of the velocity there. That is about a intramodal dispersion. And we say that a intramodal dispersion, if we use a fiber, pure silica, then we have the at 1330 or 1300 nanometer of a wavelength. If we have a source of 1300 nanometer of wavelength, then this intramodal dispersion will be zero here. Then we have seen the intermodal dispersion. So intermodal dispersion mainly it will occur in a multimode fiber. Intermodal dispersion, no intermodal dispersion is single mode fiber, but there will be intermodal dispersion in a step index and a grade index fiber. So that intermodal dispersion will be large in a step index fiber because it has a constant refractive index throughout the core. But if in the case of a refractive index in a gradient index fiber, it is not a constant. So that's why the intermodal dispersion for the gradient multimode gradient index fiber is small. So that's why we say that to reduce the dispersion, we need to use the optimum refractive index, and that optimum refractive index is nothing but that index profile of your fiber that will be in a parabolic in nature. So in that case, index profile that will be alpha is equal to 2 in a gradient index fiber. So then that index profile will become say parabolic in nature. So that's why at the alpha is equal to 2, we can reduce the intermodal dispersion there. Now next factor is about we say that a given particular source propagating the signal. So that's why we need to know about that what will be the polarization mode dispersion. Polarization mode dispersion. In general, a wave theory that polarization is nothing but a component, vertical component or a horizontal component of electric field, or you can say that a nature of electric field component, nature of electric field component that gives us the polarization in the wave theory. But here we have a ray theory. Rays are propagating means we can say that we have a source, and the source that can be a LED source or a laser source. Means light launches inside the particular fiber that will propagating through the fiber, and then at the end we have the detector. Detector receive the signal here. Now in the case of a source, we say whether it can be a LED source or a laser source. So in that case, rays are propagating through the fiber, and if you see that rays, because of the nature of a fiber is a circular, we say that core is a circular in nature. So you can see that rays may be a vertical in nature, or rays can be of a horizontal in nature. If we say that a direction of propagation of wave in z direction, then we can say that there will be field component of y and there will be field component of x inside the particular fiber there. So for each and every ray, they are propagating through the fiber. They have some particular phase constant because Generally, we say that a fiber is in a cylindrical in a nature. So when we launch power or a input inside the particular fiber, so that fiber does not maintain the polarization. This fiber does not maintain a polarization because of that fiber doesn't have the constant nature. That fiber doesn't have the constant cylindrical in nature. Okay, so that's why it doesn't follow the polarization. So now we say here whatever the rays are propagating through the fiber, so there that intensity, okay, we can say that's about because of that particular intensity of this particular light propagating through the fiber, and that will gives us the what will be the rays are propagating through the fiber and what will be the polarization of the particular fiber. So because of that changes in the polarization in the fiber, and that will be depending upon that what will be the rays are propagating in the direction of y and y in the direction of x there. So inside a particular fiber, we can define the polarization for a given particular fiber with respect to the modal birefringence. Modal birefringence. That is about a modal birefringence, and that will be about a beta f. And that is depending upon that what are the various modes propagating in with respect to y and x, because they have the because mode is propagating in that case they have the difference in a phase. So that's why the birefringence is depending upon that what will be the phase difference in that particular component with respect to factor of a wavelength there. Because we say here the lambda is nothing but a your light rays having the wavelength, and that wave we say that they have the different propagation constant, or you can say that a mode have a different propagation constant beta x and beta y because rays are propagating through the fiber along with the x direction or y direction. Similarly, we say that is about a polarization. That will be in the case of we can say that polarization will be a vertical or polarization will be horizontal because rays are perpendicular or a parallel there. Now, if you see the light launches inside the particular fiber, they have the axis, or we can say that rays are propagating is supposed to be it is in a linear mode. Generally, we say that there are the types of propagation. We can say that horizontal, vertical, or a linear propagation. So, if we say that a linear, it makes an angle theta. If we say vertical polarization, it will be perpendicular, which makes an angle 90-degree with respect to ground surface. If you consider in terms of a wave theory, and ray is parallel there, that is about a respect to the ground here. But in the case of a fiber, that rays we consider it is to be a linear one, and it is propagating through the fiber. It makes an angle theta here. So at some particular distance, again we'll get that rays that makes an angle theta here. Because when ray is propagating through the fiber, that nature of that ray will be changes. It may be elliptical, it may be in a circular fashion, or likewise. Okay, so we can have the nature of a ray propagating through the fiber, but at some particular length, that rays have the same nature, or you can say that it is in a linear nature. So the distance where we are getting that nature of a ray is the same, and that distance is called as a bit length. That is called as a bit length. Means a at the initial position, if you see that rays are propagating through the fiber, they have changes inside the fiber. If you see that initially we say that it will be in a linear in a nature, and then it will be in a circular in nature, and then again linear in a nature. So that is the length. We can say it is about a bit length, or it can be a elliptical in shape, or we have the rays. They are changing the position of or orientation of the your rays there. So that is about the from the observer point. If you see that ray will makes an angle theta here, but at a distance of some particular, suppose if you say that at a pi by 2, it will become say circular 1. Here a pi by 4, it will become say elliptical in shape. Likewise, and then at a twice pi here, that will be the same, or it will be the linear one. So we can say that after a twice pi of a value, okay, or a period, means you can say that we have the phase changes at a pi by 2, then 3 pi by 2. Okay, suppose at a 3 pi by 2, it will be again a circular there, and then a twice pi, then it will be in a linear in nature there. So in that case, which will get the linear polarization when we have the phi will be equal to a twice pi. So that's why that particular length is nothing but a bit length, and that bit length is depending upon that what will be the birefringence of a particular fiber. Means we say here the phase coherence is maintained over this coherence length, and that is called as a bit length. And that bit length, or you can say that a characteristic length, is depending upon that birefringence of the given particular fiber. Or we can write twice pi by beta x minus beta y, because we can say that phi of LB is equal to beta x minus beta y, have LB here, and that will be equal to twice pi. Now, when we couple a fiber, so we should know that what will be the mode field diameter of a fiber here. So mode field diameter is depending upon what type of a source we are using, whether we are using a LED or a laser here. So mode field diameter means what? When we launch a power inside the fiber, so this is about your core, and this one is about a cladding here. one is about axis. When we say that a power launch inside the fiber, it will looks like that nature of a signal will be looks like maximum here at the center. Here at this it will be a maximum. But some of the power is radiated in the cladding. But effective width of the source will be likewise. Okay, effective width of the source is likewise. Or in another case, if you say that if I make it vertical here, so it will be looks like we have the source and that effective width of the source, because your source is that light is propagating through the fiber, and this will be the effective width, and this the particular diameter, that will be nothing but the mode field diameter of the given particular fiber. When we couple the fiber, so in that case, that mode field diameter of fiber 1 is equal to the mode field diameter of fiber 2. If that mode field diameter of fiber 1 and fiber 2 is equal, irrespective of the diameter of a fiber, okay, irrespective of a diameter of a core of a fiber, means you can say that suppose this one is about a diameter of fiber d1 and this d2, even if the d1 and d2 is not same, okay, the diameter of a core of a fiber, the d1 and d2, even if it is not same, but their mode field diameter or mode field diagram is the same, okay, if this mode field diameter is the same, so in that case we can couple the power from one fiber to the another fiber. Means coupling of a power from the one fiber to the another fiber will be takes place if that mode field diameter will be same there. So that loss, if that mode field diameter is not same, so in that case that loss will be is equal to logarithm of 2 by 2. We can find out mode field diameter of a 1 divided by mode field diameter of a 2 plus mode field diameter of a 2 by mode field diameter of a 1. So if that mode field diameter will be 1, then 2 by 2, okay, 1, and logarithm will be 0 here. So that loss will be 0. Means coupling loss, if that fiber core, when we couple the fiber, okay, if we see that we have the fiber, when we couple the two fiber here, so in that case, if fiber have the, generally we say that they have the same numerical aperture, or you can say that both the fiber have the same acceptance angle, then and then it follows the coupling. But in another way, we say that for a given particular fiber, what will be the mode field diameter? So according to that, we can couple the fiber easily there. So that is about a coupling of a fiber takes place if I have the a mode field diameter will be matches with respect to the two fiber. Now then we will consider here what are the a fiber joint, or what are the various connectors we are using, or you can say that a connectors, fiber optical connectors, or we will learn here a joint and a coupler. Connector means joints, and coupler means what? we are connecting the two fiber. We are connecting the two fiber here. This is about a connection of the two fiber takes place. So how many connectors we are using, or how many joints we are using for a given particular fiber length, it is depending upon that what will be the total length of the fiber, or what will be the link length of the fiber. So link length is depending upon that at what particular length of the fiber dispersion will be large or distortion will be large. In that case, we are using a repeater there. So after the particular length of the fiber, we need to use a repeater, and then we need a connector here to couple the power from the fiber to the repeater, and then a repeater to the fiber likewise. So then we should know that at what particular length of the fiber there is no distortion occur, so that we can use the repeater. Or supposed to be we have a two particular fiber, it's supposed to be break here, we can join these two fiber using the slicing technique, or we can use the jointing technique there. So there are the types of fiber joints that will be join a two fiber using a splicing technique or splices, or another technique is to join using the connector there. Joining the two fiber, either use a splice or we can use a connector, so that we can join the two fiber there. So connector means what? It can be easily removable. Okay. Once it is fixed, so we could not remove that. Once we have connect the two fiber, that connector will not be removable. Means we can say that a demountable fiber connector, demountable fiber connector is to be used to joining the two fiber there. And here the splicing is nothing but a permanent join between the two fiber, and that is just like we are soldering a wire in electrical technology, that is soldering joint in electrical engineering. It's similar to the splicing technique. Means splicing means what? We are just connecting a two fiber, just like we are soldering the in a electrical there. Okay, and this demountable connector, this is just like a we can remove it also, or we can connect it to fiber for particular use, and we can remove it also. So means just like it is just like a analogous to the electrical plugs and a socket there. We can connect it to fiber, and once it is the use is over, we can remove it. Now we will learn that how these two fibers are joining together. So when we are connecting a two fiber, so in that case we need to match the what will be the core size of a given particular fiber. And another thing is that we need to match the refractive index of a given particular fiber. And then we can connect a two fiber there, and then even if we connect a two fiber with the same value, even if there may be a losses, and that losses occur at the interface between these two particular fiber. Why these losses occur? When we connecting a two fiber, this is nothing but one end of a fiber, this is another end of fiber. If that end, if it is not smooth, okay, if it is not smooth there, if it is a rough surface, the two fiber have the rough surface, so then at the interface, when we connecting to the two fiber, because of that rough surface, so there may be a losses. That is about the one case. Means we can say that is about a due to a rough surface, there may be a losses. Another thing is about what, when we have a given particular fiber, if that axis of the fiber are not match, fiber 1 and this is about the fiber 2, if that axis of the fiber is not matched, then because of that axis is not matched, so coupling, mode coupling will be difficult. So that's why these two fiber, they should be a perfectly aligned when the fiber 1 and a fiber 2 matches their axis. Okay, so then signal will be propagating through the fiber. If that axis is not matched, so signal will be reflecting from this at the interference there. And that's why that particular joint of a fiber, that losses occur at that particular joint. So that's why we need to know, we need to match the axis of the given particular fiber. Then again, these two fiber, they should have the same refractive index. Now if the refractive index is not matched, then what will happen at that particular joint or at this particular interface between the fiber 1 and fiber 2, there may be a variation. Because of that variation in the refractive index, so then at that particular joint losses will occur. Or if even if the two fibers are not matched, there may be a air in between that, then there will be, they at the interface between the fiber 1 and fiber 2, air will be the medium, and because of that air, there may be a small refraction or reflection occur at the interference. So we should know that what will be the core of a fiber and what will be the refractive index of core and all. So we can find out the what will be the power refraction occurs at this particular joint because of that area. So that's why the loss at this particular interference is depending upon that what will be the total value of that refraction occur because of that air medium. So that's why the Fresnel reflection constant is to be obtained. So that's why that loss is depending upon that 10 log of 10 with respect to that Fresnel reflection constant. That is about a R. And that R is depending upon that what will be the refractive index of the fiber core and a what will be the refractive index of this air. And that will give us the reflection, Fresnel reflection constant at the fiber interface. Okay, at the fiber interface there. So that Fresnel reflection constant, because we have the gap in between the two fiber, so that's why there will be a loss. So that's why we can use or we can remove this Fresnel reflection constant by using the connecting the two fiber or splicing technique or this particular joining the fiber. You may add some fluid to match the refractive index of the fiber there, so that loss will be minimum there. Or due to this misalignment, so then that loss will be occur. So while joining this two fiber, if that core and cladding diameters are not matched, so then we are not able to join the two fiber. If they have the different numerical aperture, or they have the difference in the relative refractive index difference between the two fiber, so then it will be difficult. You can say that in numerical aperture, then diameter, then you can say that they have the refractive index profile if it is a graded index fiber. So if that refractive index profile is not matched, or they have the different refractive index profile of the two fiber, if the two fibers are not in a cylindrical shape, that core of a fiber is not in a cylindrical shape, or that particular core will be in elliptical nature, so at that particular place, or a fiber faulty fiber because of that not a cylindrical shape, perfect cylindrical shape. So that's why that loss will be occur when we join the two particular fiber. So these are about the factors. So that's why these are the various factors. That's why that loss will be occur when we join the two particular fiber. So then we can remove this losses by perfectly aligning the two fiber. So generally we say that if two fibers are connected, okay, if their axes are matched and their core and cladding, the diameter is to be matched. Okay, these two fiber will be connected because they match their axis as well as that particular core there. If that axis is not matched, this is nothing but a fiber we have. One fiber is about the axis of a fiber, and we can consider that this is about a core we are expecting. But in the case of a fiber, there is a small misalignment. Okay, there is a small misalignment in the axis here. So this one is about the fiber axis. There is a difference in the fiber axis of these two fiber. So we are not able to join the two fiber there. If here that axis is a match here, if that axis is not matched, so then it is difficult to the matching the fiber. Then that surface we say it is about a smooth one. If it is not exactly smooth surface, likewise, if it is not exactly a smooth surface, a small difference in the axis or misalignment at this particular surface. Suppose fiber 1 has this particular axis. Likewise, we say this is about a fiber 1, and we have the another fiber. When we joining the fiber, this one is about the axis of one fiber, this one is about the axis of the another fiber. There will be the angle between the core axis. Then that losses will be occur. That's why the axis is to match. When we connect the two fiber, if there will be a separation between the two fiber, there will be separation between the two fiber, then fiber could not join. If that axis is not matched, if that core axis makes an angle, So then that is called as the angular misalignment. This one is about a longitudinal misalignment. So that's why we are not able to connect the fiber there. So we can say that another thing is about what? That is a core diameter mismatch. Okay, core diameter mismatch. So fiber has a core diameter and another fiber is has a large core diameter. So this is nothing but a core diameter mismatch. So that's why we are not able to connect these two fibers there because there is a mismatch in the core diameter. And at the particular interface, we can say this is about a core of a fiber. This is about a cladding of fiber. And that acceptance angle of this particular fiber is different. So then we are not able to, this is about a theta, this is about small theta, this is about large theta. So we are not able to connect the two fiber there. And then the refractive index of this particular fiber is not matched. If the core profile is not matched, if it is alpha is equal to 2, if we can say it is about a gradient fiber with a parabolic profile. If that is not matched, so then we are not able to connect the two fiber there. So we use a technique to connect the fiber, a fiber splices. And this joining the two fiber using the splicing technique is a permanent in nature. So permanent means two fibers are connected permanently by soldering or by heating. So we can connect the two fiber. Okay, we can say that both the cores and everything is matched. Then and then we can connect the two fiber by heating the two ends of the fiber. That's why we can connect the two fiber. But in that case, when we heat, the surface is to be smooth, and to get the smooth surface, we need to cut the fiber end using the technique knife edge initiative crack propagation at a curve model. We can cut the fiber or we can break the fiber using the knife so that a surface will be a smooth there. So means that core will be fixed, no core angle will come. So that's why it will match here. Another technique is about to joining the fiber. We can use a fiber fusion technique. With two ends of the fiber, we have the electrodes here. We just create an arc in between these two electrodes so that these two fiber get heated and they will be connecting together there. And that is about a splicing technique. Another technique of a fiber here, we just connected two fiber there. So that is about a electrode. Just like we have the arc between the fiber will generate and then it will automatically connect the two fibers. So that is about a fiber technique there. We have the core and cladding is not matched, then we are not able to connect the two fiber there. And here again another is about a mechanical splices. We can connect a two joint. This is about a mechanical structure. We just okay insert the fiber one end here, another fiber from this end. Okay, and then we can in the initial internally it will be joint here. So if you see this cross section here, so they are joint here. So we can connect it to fiber using a splicing technique, or we have the another technique about a splicing here. We create a groove here, and using the heating here, we can connect a two fiber there, or a we have a elastometric fiber splicing technique, or this just like a joint two fiber, then connect the glass here, joint two fiber, and then we have a flat glass plate, and then we need to connect the fiber inside there. So that's about a technique of splicing here. So we can connect it to fiber using the different technique, and that is about a fiber splicing. So we can use a various fiber connectors. These are about the a fiber connector. We can use here the fiber connector. Okay, so this is about fiber ends are connected, and they have the ferrule connectors. We can say that is about a ferrule connector here. So one cable terminated here, another cable is here, so we can connect it to fiber using the ferrule connector. So another is about a stainless steel ferrule here, and we can connect a two fiber using the connecting the two fiber using the this way here method using the ceramic capillary tube. Here we have the ceramic capillary here, ceramic capillary failure. We have the fiber one and another fiber. We can join the two fiber using the connector there. So we can connect the fiber. We need to match the core of the fiber, core interaction type or a surface interaction type here. That is about the fiber types. We can use a connector to splitting the power or to combine the power. So there are the splitter, combiner. We have a coupler, power coupler, star coupler. So we have the wavelength division multiplexing there. Okay, wavelength division multiplexer or wavelength division demultiplexer here. That is about the various optical fiber coupler, and that coupler have the various functions. And that is about the end